Hey guys, Ms. Peterson here, and welcome to AP Physics 2, Lecture 2-1, where we're talking about heat, temperature, and energy. This is our first unit, our first lecture from Unit 2, Thermodynamics. We're going to be talking about really the differences between heat, temperature, and energy, because you might have used these terms interchangeably in previous science classes. And we'll also talk about kinetic molecular theory. Before we get to that, though, let's do a quick review and make sure we're all on the same pages with the states of matter. Okay, it might have been a while since you learned these. So as a reminder, in a solid, the molecules are just vibrating in place. Okay, they're just vibrating in place. And then as you give them more energy, they might turn into a liquid where the molecules are rolling around each other like in a mosh pit. And then if you give them even more energy, maybe you got a gas and the molecules are zipping around and flying all around. So because of these interparticle interactions, because all of these ones are touching and all of these ones are touching and interacting, and then these ones are not really interacting, that gives solids, liquids, and gases some of their properties. Some of the main ones being, okay, solids are rigid, okay, and they have a defined shape and volume, okay. They're always going to take up the same amount of space because they're solid. Where liquids do not have a defined shape, but they do have a defined volume. Okay, they will take the shape of whatever container you give them, but their volume will not change. Where gases are compressible, okay, gases can compress and expand. They do not have a set volume. They expand to fill their containers. Okay. And just so that we know our vocabulary, let's review the names of all of the phase changes. When things go from a solid to liquid, we call that melting. When things go from liquid to gas, we can call it boiling. But sometimes it happens really slowly, and we call it evaporation instead. Yep. Now going the other way, removing the energy, going from a gas to a liquid is called condensation. Okay. And going from a liquid to a solid is called freezing. And every now and then you'll see it called solidification. Now this normally depends on what time scale you're doing it on. If it occurs really fast at a cold temperature, we call it freezing, where if it occurs more naturally over a longer scale of time, we tend to call it solidification. And then we can add in the bonus ones. Okay, going from a solid to a gas, it is sublime. It's called sublimation. Okay. This is what dry ice does. Sometimes this happens when snow evaporates a little bit, okay? And then going from a gas to a solid, this is what happens when frost forms on your window on a cold day. That is called deposition. The gas is getting deposited in the form of a solid. Okay, cool. We know our states matter. Yeah. This unit, last unit we were focused mostly on liquids. This unit, we're going to be focusing mostly on gases. Okay? And with the gases, we will often talk about their temperature. So temperature is average kinetic energy. Temperature is the average kinetic energy of the motion of the particles, atoms, or molecules. Temperature is average kinetic energy. Temperature is average kinetic energy. So faster movement means faster, means a higher temperature. Okay? The units that we use in this class, for all of our calculations and everything, we will want to be in Kelvin. Okay, Kelvin is an absolute temperature scale. It is based solely on the motions of molecules, which is cool because then basically absolute zero is 0 Kelvin. That's the temperature at which all molecular motion stops. Okay, so a consequence of this, if all molecular motion stops at 0, you're never going to have a negative Kelvin. Okay, all of the atoms are always going to have some kinetic energy, so there's always going to be some Kelvin temperature. But we do see negatives in our other temperature scale, degrees Celsius. Now, the Celsius scale was based off water, okay, where 0 degrees is the freezing point of water. And 100 degrees is the boiling point of water. Okay, that's what Celsius was based on. So because we need things in absolutes, we're always going to want to use our Kelvin scale. And the conversion is that the degrees in Kelvin are equals to the degrees Celsius plus 273. Technically 273.15. But yeah, that is the conversion. And you do, let me double checking your guys' AP Physics 2 reference sheets. I believe, yes, you do need to memorize that conversion. Okay, so this is a memorize thing. However, most of the time we'll be talking about differences in temperature or delta T. And because the conversion is just an addition of 273, delta T will always be the same in Kelvin and degrees Celsius. So if you're looking at a delta, don't feel a need to convert, okay? Cool. Okay, cool. Now, let's look at these. These are called Maxwell-Boltzmann distributions. And what they show is the distributions of molecular speeds in a sample of a gas. So in gas A right here, okay, this is the same sample, but at different temperatures. So what you'll notice is that at the higher temperature, okay, the speeds are more distributed. So it's not that all of the molecules are moving faster, it's that they have a wider range of speeds available to them. This also explains why if you leave a cup of water out, okay, it will eventually not be there anymore. It'll eventually all evaporate. Okay, the boiling temperature is 100 degrees. And no, like my glass of water is not going to be at 100 degrees at any point while it's evaporating. But a small portion of the molecules might be. So that's how that works out. Okay, the speeds are more distributed at the higher temperatures. Okay, it is an average. Okay, cool. Okay, cool. Where in this one, okay, these are all at the same temperature, but they have different masses. Same temperature, different samples, different gases. Now, if they're all at the same temperature, they should all have the same kinetic energy. But we have to remember that same temperature does mean same kinetic energy. But kinetic energy is 1/2 mv squared. So since hydrogen has the smaller mass, smallest mass, okay, its mass is the smallest, it will be moving the fastest. Okay, cool. Okay, cool. So let's go ahead and talk about the different variables that we use to describe gases. Okay. Now we will use pressure. Okay, we've already talked about pressure. That's what all last unit was about. We use units of pascals. And again, this is the force due to particles colliding with walls. Okay. And then we'll talk about the space the gas takes up. Okay, that is the volume. We'll typically use units of meters cubed in this class, not the liters or milliliters that you might use in a chemistry class. But again, it's just the space taken up. Now, this is normally determined by the container, or it's always determined by the container. Which brings us to the number of moles, okay, which uses the letter N. If you've taken a chemistry class, you probably know what a mole is. If not, I encourage you to watch my little short, like 5-minute lecture on it. I'll link it in the description. But what a mole is a number, okay? On your equation sheet, it's N naught. This is called Avogadro's number. And it is 6.02 times 10 to the 23rd. And what this refers to is how many atoms or particles or molecules there are per mole. It is a really, really big number because atoms and molecules are really, really small. So when we count them, we tend to count them in moles of atoms or molecules, which is this many atoms or molecules per mole. So not atoms over molecules, atoms or molecules. Clarify that. Now, if we ever needed to find the number of moles, okay, N is just like equal to big N, which we use for number of particles, divided by Avogadro's number. Okay, cool. If we're talking about the mass of a sample, we'll talk about its mass in kilograms. Okay. Yeah, it is just the total mass of the sample. Normally when we do this, we'll make sure not to include the container that it's in. And then temperature, which we use units of Kelvin, is the average kinetic energy. Okay, so that is some of the vocabulary that we will use throughout this unit when we're talking about gases. Which, now we got temperature, we got some of the volumes that we need to describe gases, but note energy isn't on there, heat isn't on there. But we're going to be talking about heat a lot this unit. So what is heat energy? Okay, we have to remember, in a gas or in any molecule, the atoms are moving, okay? They're moving. And when they move, they bounce into each other, okay? And when they bounce into each other, they transfer energy in an elastic collision. So what does an elastic collision mean? You might remember from a previous physics class, but elastic collisions are the bouncy ones, okay? So in an elastic collision, it bounces off. And because it is an elastic collision, it follows two very important conservation laws. The first one being conservation of momentum. So each molecule conserves its momentum. Remember, momentum uses a p, and it's equal to the mass times the velocity of the particles. And because it's elastic, we will also have kinetic energy being conserved. So we have no loss of energy there. And that's important, okay? This is why things can transfer their energy through those collisions, is because that kinetic energy is conserved. Now, particles tend to move more when they're in a hot object, okay? Higher temperature means the molecules are moving more. And if they're moving more, they're going to collide more. And if they collide more, they transfer that energy, okay? The cold molecules maybe aren't moving as fast. And that's because of that random motion, because of that conservation, there will always be a net transfer of energy from hot to cold in those collisions. The high energy ones are going to collide more with those low energy ones and transfer and share that energy. Okay? And we call that transfer of energy heat. Okay, so that transfer of energy is called heat. It is the transfer. Heat can be lost or gained, but we will never say this has 30 joules of heat. No. Okay. Rather, we would talk about its internal energy, which in some cases you will see this called thermal energy. Okay, so when you see thermal energy, think internal energy, not heat. Internal energy, which we use the letter U for, is the sum of all of the energies of the molecules. So heat is that energy that's transferred, but if you're talking about a substance, it gained that energy. So that energy became part of its internal energy. So it would be correct to say a sample has 3,000 joules of internal energy, okay? And we typically just count the kinetic. Now, if we have two things that are at the same temperature, we call that thermal equilibrium, okay? Now, that just means that the net transfer of heat between them is zero, okay? The collisions are still happening. Yep. So, make sure you got this. Go ahead and apply this and see if you can think of a good example to explain this to someone. So one of the classic examples used to explain this is the ice sculpture versus the match. So I want you to picture right here, I have a big giant ice sculpture. See it? Yeah. Okay. And then right here, I have a tiny little match. See it? Yeah. Okay. Now, can my match melt my ice sculpture? Do you think I could use the energy of this match and gently melt my whole ice sculpture? Probably not. Okay, it's probably going to take a lot more than one match to melt a giant ice sculpture, because even though the match is obviously at a much higher temperature, the ice sculpture has a lot more internal energy. It still has more thermal energy inside of it, okay, from all of those individual particles just vibrating in place. The match has a lot more molecules and they're moving crazier, but it's still not enough to melt the giant ice sculpture. Okay, cool. Okay, cool. Which brings us to entropy. Entropy is another quantity that determines how energy moves through objects. And basically, you might have heard entropy described as the randomness of something, but that's kind of a simplified version and not really good for us in this class. Okay, we want to think of it as the arrangement of the energy in a system. If there's more possible arrangements, more ways that energy can be spread out, or if that energy is more spread out, sometimes you'll see them called microstates. Those arrangements are called microstates. Okay. If you look at this example over here, there's 1, 2, 3, 4, 5, 6 places that the energy could be. So if it was all on one side there, we would say it's a lower entropy, where if the energy was more spread out, it would be a higher entropy. And anytime there's more spaces available, more way for it to spread out, that is a higher entropy. And the universe tends toward higher entropy. The nature of things is that energy gets dispersed and spread out. Okay? Hot coffee cools and releases its energy to the environment that used to be contained just in it. Okay? Processes that decrease entropy, that make things more ordered, those are always going to require that we do work. Okay? We have to do something to make it more ordered. It won't just naturally happen that way. But heat does naturally move. And how does it move? Okay. I just went and grabbed my cold coffee. And as I hold my cold coffee, there is physical contact between my hand and the cup. So my hand is warmer than the cup, so it is going to conduct heat to the cup. Conduction is that transfer of energy due to direct contact. Okay, this is actually the molecules of my hand colliding with the molecules of the cup. Now, we will often talk about the rate that this happens. Okay, conduction is the only one that we're actually going to do math with in this class. And it is our next equation. Okay, next equation on your equation sheet, right under Bernoulli's principle. And it is that Q over delta T, so heat over some period of time, equals K. Now, K is the thermal conductivity constant. Okay, thermal conductivity constant. It is dependent on the material of the substance. Okay, each material has its own thermal conductivity constant. If it is a higher number, that means it's like a metal. It is good at conducting heat. If it's a lower number, it is an insulator. So it is not as good at conducting heat. Okay, so we have K times A, which is the area of the surface that it's exposed to, times that change in temperature. See, a place where we won't care if we're in Celsius or Kelvin because it'll be the same. That's the difference in temperature on the two sides of whatever the heat is being conducted through, over L, okay? And L is the length of the path that it travels, but you can also just think of it as the thickness, okay? So add it to our list of variables for distance. We got H for depth, and we got Y for height, and now we got L for thickness, okay? Totally makes sense, but hey, I didn't write the AP Physics equation sheet, and it makes sense. It is the length of that path that it's being conducted through. Now let's look at this equation again. Now let me finish. Temperature, okay, A is for area, K is for that thermal conductivity constant, Q is for heat, T is for time, okay, and remember heat is in joules and time is in seconds, okay, area will be in meters squared, temperature in Kelvin, and thickness in meters. But let's look over here in a second at this heat over time, this joules per second, the rate and the change at which that energy is flowing through. What does that also mean? Might be a familiar concept. We have joules per second. What does that make you think of? It's the power, okay? one way you can think of this equation, this heat over time, okay, that is P, the power of that conduction, okay? Now, power, remember, is in units of what? Yeah, what? It's the watt, okay? Is in units of watts, where we remember that 1 watt is 1 joule per second. Okay, cool. So the other two ways that heat energy can be transferred is through convection. Okay, it is a transfer by the flow of the matter. Now, somehow I missed a sentence here. Okay, this can be forced like in a convection oven, like your air fryer, or it can be natural, like in weather or currents in the ocean. Okay, but basically, it's due that a change in temperature when you heat something up, it tends to make things less dense. So if we have less dense air, the buoyant force will float it to the top of the container that it's in, where it'll be maybe away from the heat source and it'll cool off and go back down, and we can get those convection currents. Where radiation is the transfer of thermal energy through infrared waves, okay? Through the electromagnetic waves being given off by the vibrating electrons in your body. Okay, cool. Now, last thing in this lecture, we've talked about temperature, we've talked about energy and all of describing gases, but there's some rules of gases that are going to allow us to make predictions. We're going to be talking a lot more about this in our next lecture, which is all about the ideal gas law. But these are the rules that gases have to follow for us to treat them as an ideal gas and all of those things, okay? And this you should memorize. AP curriculum loves to ask questions that rely on your understanding of kinetic molecular theory. It'll show up in one multiple choice question on the test. But basically, if we're talking about a gas as an ideal gas, its molecules are in continuous random motion. We got lots of molecules, okay? It's a big number. A mole is a lot. It's a big number. The separation between them is extremely large, so they're super small compared to the spaces between them. They do not interact with each other, okay? We're not going to ever consider the gravity that two atoms in a sample of gas exert on each other, or the electrostatic repulsions of their electrons. Okay, we're just going to ignore that. And all collisions are completely elastic. Okay. Now, because of these, that will lead us to two of our big equations about gases. The ideal gas law, which again, all of the next lecture will be around the ideal gas law, so we'll talk about it more there. But it is PV equals nRT, or you might see it, or NKBT, okay? Where, remember, P is pressure, or let me just label the ones that are a little bit different in here. R is the gas constant. Okay. And it is on your reference sheet. It is 8.31 joules per mole Kelvin. Okay. Now, oh, and then N, of course, is the number of moles, in case you forgot. Where big N is the number of particles, okay? So not Avogadro's number. And that can be easy to remember because of KB. KB is Boltzmann's constant. Okay, this is also on your reference sheet, but it is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. Notice the moles is missing, okay? Because Boltzmann's constant is just equal to the gas constant divided by Avogadro's number, which you can kind of see in that times 10 to the 23rd. So it is more specific to like individual particles. And that's why in this one, the ideal gas law, you'd be multiplying it by the number of particles. But there's another equation on our equation sheet that we'll use on occasion for internal energy, okay, or kinetic energy. Actually, I'm going to call this one thermal because we're talking specifically about the internal kinetic energy of a particle. And that's K equals 3/2 Boltzmann constant times that temperature in Kelvin. And this K is for the kinetic energy. So that we can use with 1/2 mv squared or with any of our heat equations to actually calculate the internal energy of a sample of gas, okay? But only in very specific circumstances. And we'll go through that more, again, like I said, in the next lecture. Okay, cool? Okay, cool.